Here are the solutions to the assessment on improper integrals of the first type. The first type of improper integrals are integrals that have one of the limits equaling infinity or negative infinity on the lower limit at times. In the first problem here, the first thing we need to do is rewrite it so we don't have infinity as one of the limits. So we're going to take the limit as some variable of our choice. I chose t here, but it could really be any variable as that variable approaches infinity. And so what we have now is a proper integral that we're going to evaluate the limit as the upper limit of that proper integral approaches infinity. So we'll go off to the side and evaluate this integral with t, with our variable in there, as our upper limit. And so the value of this integral depends on t and is going to be equal to this 1/2 minus 1 over 2t squared. And so we now evaluate the limit as t approaches infinity of this being the value of this integral right here. And plugging in infinity there, we get a term of 0, so we have 1/2 minus 0, which is 1/2. So in this problem, points were given for the final answer, also for writing the integral as a proper integral, or the limit of a proper integral, and then also for evaluating that definite integral with the variable in it. In the second problem, we have negative infinity as our lower limit. So again, we're going to rewrite it using a limit. And so we're going to evaluate the integral, the definite integral from d to 0. D was my choice of an integral here, or of a variable, sorry. The integral, or the antiderivative of 1 over x minus 2 squared is going to be negative 1 over x minus 2. You can get this by using the power rule, rewriting this expression as x minus 2 to the negative 2. And then when we evaluate, we get this 1/2 plus 1 over d minus 2. So now we go back and we evaluate the limit as d approaches negative infinity of that expression. And plugging negative infinity in, we get 0 for that term, and so we get 1/2 again. Points were given for the final answer of 1/2 for rewriting the integral as the limit, as the lower limit approaches negative infinity, and then for the evaluation of the definite integral with that variable in there. And then on the third problem, we have an improper integral because both limits approach infinity, one negative infinity and one positive infinity. So what we have to do here is split the limit up into two separate limits. We have a choice. We can use any constant that we want as our upper limit here and as our lower limit here. I chose 0 because 0 tends to be easier to work with. And I used two separate variables here. It would be proper, if you would like, to use the same variable. Just understand that if we use I approaching negative infinity here and we were to use I approaching positive infinity here, the I in this term, this entire term here, would be different from this one. I like to use different variables just to not get them confused. Since the integrand is the same in both of our definite integrals, I'm going to evaluate the indefinite integral first, or just an antiderivative, and integrating by parts, we end up getting negative e to the negative x times x plus 2. Depending on how you simplify, you might get different expressions that are equivalent to this. I factored out the negative e to the negative x from the two terms here. You certainly wouldn't have to do that to get the correct answer. So putting that into each of my limits, we're going to evaluate both of those definite integrals using our variables. And so we get an expression that looks like this. We'll notice here that the negative 2 term here and the positive 2 term here are going to end up canceling each other out, and that's because those are coming from the 0 here and the 0 here. So that is what we would expect to happen there. It's what happens as we approach infinity that's going to be interesting to us. Since we get infinity times negative infinity in this first limit, this limit right here is going to diverge, which means that the entire integral is going to diverge. It is not possible for one of them to diverge and the entire thing to converge. One thing I want to note is that this term here in the second limit is going to equal 0 due to L'Hopital's rule. We don't need to evaluate that though because the other limit, the first limit over here, diverges. So points in this problem were given for the final answer, saying that the integral diverges. For rewriting this as two separate limits and breaking up those two limits appropriately, and then also for evaluating the antiderivative of that integrand.